Welcome everyone. Herzlich willkommen. Who's here for the Digitaltechnik? Sorry, Language. Wer ist hier für Digitaltechnik? Und einige andere sind im anderen Raum. Können wir die auch sehen? Ich sehe gar nichts, aber... Hallo? Nein? Ja, okay. First of all, language. We are going to hold this language in English. Is that okay? The other alternative would be Turkish. Türkçe bilen? Oh, look at that. Okay. So, welcome. I'm just trying to get the microphone set. So, welcome to the Design of Digital Circuits, first lecture. Important thing is this lecture will be given by Professor Onur Mutlu. He's a professor at the Computer Science Department, also an adjunct professor at Carnegie Mellon University. And, you know, you could say that he's one of the most cited, most well-respected researchers in computer architecture these days. And that's not me. Okay? So I just fill in during his absence, and this is a problem of having someone who is very famous giving you the lecture. It's actually a great opportunity. However, there are some obligations that come with it, so he had to be in the United States for a talk. And he was very sad that he could not show up, and he said, Frank, go there. And my job is to fill in. This will not happen very often. Maybe one more time. So this week I'm here. Next week and the following weeks, Onur will be giving the lecture. So don't worry, you're in good hands. Just today you have to do with me. So who's this guy? My name is Frank Gurkaynak, and those of you who speak Turkish realize I'm also Turkish. We're not related. We didn't come here as a gang. True. I work at the electrical engineering faculty with Luca Benini, and I will also bring you a little bit of the electrical engineering perspective. I know you're all computer science students, and if you wanted, you could have easily gone to the other building and sit in electrical engineering classes. So you did not do that. There's a good reason, because you thought electrical engineering is not my thing. I want to study computer science, and here is an electrical engineer coming here and giving lectures. Don't worry, we are just going to give you the perspective. You're just going to get the nice bits of electrical engineering, just the interesting parts. And just what I do, I also design, I design and teach how to do integrated circuits, very large-scale integrated circuits. We have a lecture series, advertisement coming now, VLSI 1, 2, and 3, because, you know, why not have a trilogy? If something is good, it sells. We also supervise and organize practical semester and master theses in the electrical engineering faculty, where you can design your own integrated circuits. My work, we actually these days work on open source hardware, so we work on what we call the PAL platform. It's based on RISC-V processors. We're all going to learn about what an instruction set architecture is throughout this thing. If you're interested in our funny mascots and things, we have a Twitter feed. And this is what our products look like. So these are microchips. And microchips is part of the thing that makes the computers tick. And this is what we want to do in this lecture. We want to learn about how computers work, what's inside. Don't say Intel's inside, right? Okay. And the next thing is actually, okay, good, there is something inside. Why we should care? This is the interesting question that we will try to answer. And today in the first lecture, I will talk about, or I will try to motivate you why it is also interesting to know a little bit more about what's inside the computer and why it will help you to be better computer scientists, computer programmers, computer engineers, by knowing a bit more than what you absolutely have to. And if you want, you can blame this gentleman over here. He's Gordon Moore. Anybody hear of Moore's Law? Oh, everybody knows that. Did you know that this is this guy? Okay, anyone? Can you say who is this guy? Yeah?
He's a co-founder of ETH.
Yes, he's a co-founder of Intel, that's correct. And being a co-founder of Intel meant that he was sitting in a lot of boring meetings, and it's a true story. And he was plotting how many transistors, whatever it is, they were able to manufacture over the years. So he had actually 5 data points. See, this is 1959, where they had the first transistor. 62, they had like 3 of them, no, 8 of them, 63, 64, 65, and there he is sitting in the meeting, and he says, oh, look at it, logarithmic scale, it goes straight up. And this is when he established Moore's law. And Moore's law, anybody know what it says? You know Gordon Moore, you know Moore's law, you don't know what it says. Yeah? Yeah, that's it. I'll just repeat, because I tried it. I cannot throw this thing, okay? I'm sorry. There is one explanation of it, is that the size of transistors will halve in area every 2 years or so, and you can pack twice as many transistors in the same area as you did 2 years ago. This means that we are increasing the integration density and things like that. The interesting thing is, it's not a law. You know, if one day comes and, you know, we had 2 transistors and 2 years later we still have 2 transistors, it's not like the door's going to open, policemen are going to come in and say, you've been in violation of Moore's law, you're going down. No, okay? It's not even a law. I mean, it's an observation. The guy was bored. And then later he actually wrote a couple of papers which nobody mentions, where it says why Moore's law will end. And until this day, it was a self-fulfilling prophecy that went on. Why am I talking about this? So this is the story. First transistor was in 1947. It resulted in a Nobel Prize. And then it took some years. The first silicon transistor was in 1954. And then the first CMOS gate, whatever they are. So they are building blocks of electronics, which we are not so much interested about, in 1963. And the first commercial chips were in 74. Now we fast forward. I just looked it up. What's the largest chips that we have? And, you know, people stopped counting them very exactly, but this is about the number. And this is like the unit that we use for counting the complexity of the chips. And it stands at more than 10 billion. You could equate that more or less to the population of the Earth. Okay, so in one single chip that you have today, we managed to pack as many people in the Earth as transistors. You can have your transistor doppelganger in a, you know, NVIDIA Pascal GPU. It's amazing where we came. I mean, it's a relatively short amount of time. Obviously, you say 1954, isn't that when Columbus went to America, you know? But it has also practical aspects. So these poor people, so that's Samuel, that's Michael. They were doing, they are in the master's program in ETH. I told them that I will put their picture up. They thought I was joking. And they are the type of nice guys, when they see a camera, they just smile. It's always nice, you know? They're not, why are you taking a picture of us? Okay, so they were working on semester thesis, and at the end of their semester thesis, they called their chip Atomario. This is an actual photograph of the chip. This is how the computer drawing of it is. And it's actually a huge chip. It has 10 million transistors. Now you might say, we could build in 2019, with the combined might of all the engineers in the world, we could build chips of 10 billion transistors. That's true, but 10 million transistors, roughly the population of Switzerland, if we are making the same approximation, is still pretty good. Especially since these were designed by 2 students, these 2 guys, that are doing that as part of a semester thesis project in 14 weeks' time, getting 9 ECTS credits, and they did not even get a 6. It's true. Well, they did not fail the class, if you're wondering. But that should give you some pause to think. It's actually amazing. I mean, this means that building a chip with 10 million transistors, which 10 years ago would be a pretty good achievement, even for a company like Intel, or 15 years ago, is now something that you could very realistically do in 2 to 3 years of time within 1 semester. It's not like you take a year off and do this all the time. So this is amazing. And the question that we should be asking ourselves is, how is it possible that, let's say, students, I mean, they are good students. It's not like we went to the street and picked the worst students and said, make a chip and get not a 6 for the work. How does this work? And the answer is actually, we use techniques that have been perfected since the dawn of time to manage complexity, divide and conquer, and the other thing is abstraction. So we make sure that there are, we have different levels and we can just concentrate on the levels that we are interested in. If you look at what we have to do, there's a problem, and somehow electrons will be used to manage this problem. In the meantime, there are all kinds of different things. You have to develop some algorithm, programming languages, system software, and somehow the software and the hardware have to have an interface. You say, this is where the software ends, this is where the hardware starts, and the computer science people and the electrical engineering people have to agree that, okay, this is the point, I make this hardware, and you will develop the compilers and things, and it will work. So this is mostly the specialization that you have in computer science, whereas when you go one level below is where you could see the microarchitecture, we'll talk about it, logics, is more what the electrical engineers maybe are doing. People can argue about that. And then if you go further down, it's actually the domain of physics or material science to make sure that you have devices that can work with it. Everyone else in the world, well, they are up there, they have their problems, and they are looking for help so that they can be solved. But the power of abstraction is important, because if we didn't have this, everyone in the world had to know everything about this. And this would make it impossible for us to develop things which have, 10 billion transistors or whatever these mysterious... I speak too much of transistors, right? Nobody's bothered? Is anybody bothered, transistors? They are all in the other room, I know. I'm very curious what's happening in the other room, actually. But, okay, I've never had a class where it was broadcast to the other side. I feel like I'm cheating them. But, okay. There are still some seats available in the splash zone. Well, okay. So, the abstractions actually allow us to concentrate our work on one level. You don't, a high-level language programmer does not need to know what the ISA is or how the transistors work or something like that. He can stay in his own domain, and he knows that he can solve his problem in that level. And this is really important because it improves productivity. You can do much more complex things. Instead of worrying about all the tiny details, what happens above your level of abstraction and below, you can just concentrate on what you can do best. And aren't you bothered by this? No? Because in this lecture I said we want to know a bit more about the electrical engineering perspective, what's in the computer. That is what I said. So why would you want to know about what happens inside the computer? You're a computer scientist, and it should be enough that you stay in those, let's say, higher levels. And, well, this is the main part, or the main message that I want to bring across. And since I'm not owner, I have to underline it all the time. As long as everything goes well and everything works, there is actually not point in knowing what happens above or below. But what if that you have a program that you want to develop and you realize it's running slow or it doesn't run correctly? Obviously, there's a bug in it, you can say. But no, I mean, you are sure that the program that you've written should run correctly, but something is not doing well. Or it's consuming too much energy, and that becomes a problem because you want to stick it in a space shuttle. Well, they don't exist. You want to, the things that go to space. And, or your system just shut down, and or somebody hacked into your system and you have no idea what just happened. And, or The other way around, you can also see what the electrical engineers have, and we have this daily, I can tell you. We have all these brilliant ideas and says, we are going to build this chip, which is wonderful, does this and that and that. And then you come to the computer science people, your future selves, and they look at us and say, yeah, cute idea, but are you kidding me? How am I going to program this? I say, oh, I didn't know, you know, I just make it and I hope that it works. And then maybe the idea was good, but you don't provide the right primitives to connect to the, you don't give the right access to the software to be able to control the capabilities that are hidden mysteriously in your hardware. So, or you are sitting there and saying, okay, we know what the computers are here today, how they work, and I want to do something better. How can you do something better if you don't know what the ones that are working currently are working? So there are two goals of the course. Onur has two goals in the course. And the first one is to understand how a processor works underneath the software layer, and how decisions that are made in hardware affect the performance of the software. Some of them are, there are problems we will see. If you try to get 10 billion things to work in concert, you will have to make compromises. And you want to have large memory, you want to have fast memory, you want to have cheap memory. Well, guess what? You're not going to have all of it. You have to sacrifice one. It's either going to be large and slow, cheap and small, or a combination of it, but not all of them. So to make practical systems at every level, not only in electrical engineering, you have to make some compromises, and you want to understand what those compromises are. And in case things change or there are new opportunities, you may want to explore different trade-offs. You say, hey, until now, we always use this one. But I know the principle what's behind it. So in this case, I want to be able to change it. It's important that you have this capability, otherwise you cannot do it. And so this brings you to the other thing, to be comfortable in making design and optimization decision, which crosses these boundaries. The most important problem is, and this will happen a lot, you are in your domain, you feel comfortable here, but in the project you're teamed up with this evil electrical engineering person, me, and you explain your idea and say, oh, no, it cannot be done, it's too complex, you don't understand it, and you know, I'm pushing my problems to you because I don't want to do the work. You know, I mean, engineering is optimizing, and the first thing you optimize is your own time. And if you can do it, you can push it to the other side. So if you cannot push back, if you don't know, I mean, it's not like you have to design or you want to do the things he does, but you should be able to understand enough of the work so that you can also go and influence those decisions and say, hey, you know, this is like that, and here, let's have a discussion, and I understand your points, and this is important. So this is our theme for the lecture. And we will always keep this in mind and come back and forth. And every now and then, when you're sitting in an exercise, and the exercise looks horrible, and you hate, can I say that? Did students say that before? No, the exercises are great. So if you really hate something there, you can go back and say, okay, this is why I'm doing it. It's only one lecture. I'll get a glimpse of what they do, I'll inform myself, and this will help me in my career, hopefully. This is the marketing part. So, anyone heard of these? Gordon Moore, everyone knows, but this cute thing, nobody knows? Oh, you're just tired of raising your hands, right? I mean, it's obvious, okay. Spectre, Melda, what are they? Yes?
They're like some kind of ways to hack a computer.
There are some security vulnerabilities in computers. Yes, that's correct. There is another one. Now, you have to say you know this. Anybody know this? Rowhammer. Any idea or any insight? What is that?
It's when you enable and disable spots in memory to quickly, it affects all the parts.
Yeah, so it's actually, I don't know how they took this picture, actually. I'm really thinking that they had actually a hammer on there and it's not Photoshop. You take a piece of memory and quickly switch it on and off, on and off, on and off, and you disturb the memory locations around it. I'm going to talk about it tomorrow, so this is going to be our talk tomorrow. And the interesting thing is, the pioneer of this attack or these problems is actually Professor Mutlu himself. And tomorrow we're also going to talk a little bit about problems of these things, multi-core systems that have a strange memory architecture and have to go through a narrow interface to an external memory to be able to read and write things. So this is what we will talk about tomorrow. And the reason why we will talk about these tomorrow is because I talk too much, make silly jokes, and the lecture drags on. No. Why we will talk about this is because these are all problems that can only be solved or that can only be understood if you are able to cross the boundaries of the abstraction that we talked about. So we stay in our boundaries, but we have to know what is happening above and below us so that we can find solutions to it, or we can find better solutions to these problems. We can make systems that do not have these problems or build better systems. Now this is the difficult part of the lecture. Let's start with some puzzles. Also, Professor Mutlu really likes architecture. I'm to blame for half of this, so let's go. So what is this? Ta-da! Yeah? Yes? No? Yes? It is Bahnhof Stadelofen, yay! Why do we have it in the class? Who was in Bahnhof Stadelofen today? People from Inti? Okay. Good. So what do it will become clear, hopefully. What do the following have in common? So this is in Lisbon, Garda Oriente. Anybody been to Lisbon? That's a great place. Anybody from Lisbon? No, okay. Anybody from Milwaukee? Another building? I told you, likes architecture. Athens Olympic Stadium? I'm losing the audience, I have to go. City of Arts and Sciences in Valencia? Yeah, you've been there, great. This is animated, see, its roof is opening and closing, Florida Polytechnic University, and the Oculus in New York City. So, what do they all have in common with Bahnhof Stadelofen? One person in the back, yes. They are all from Calatrava, who's a famous architect, and he's from the ETH, alumnus. And Bahnhof Stadelofen is one of his earlier works, and the Oculus in New York City is one of his later works. So they were all designed by him, and if you looked at, I mean, there's a reason why we are showing this, okay? Trust me? Trust? No. Okay, I'll take that. You can see also in his earlier work, there are some common things in the way he designs the buildings. I mean, if you go all over the world and you see some structures, sometimes you will say, this must be a Calatrava building. Somehow, I mean, you haven't seen maybe the drawing before, maybe you're very interested in architecture and buy these big glossy books. They sell always 50% off. And you know them by heart, but sometimes you just say, hey, I think this is this one. And not only for Calatrava, there are different architects, they have all some ideas. They follow some design principles. So this is him. So this is your first design assignment. Go and find the closest Calatrava building to this classroom. Anybody know what it is? The library, yes. It's about 300 meters from here, or 400. Okay, if you really like a challenge, go and find the one which is furthest away from this classroom. And I think it's in Argentina, but okay. So, think about the trade-offs in the design. You know, what is what did the architect do about it? I mean, the library actually is a more modern building that he made. Stadelhofen might be a bit more utilitarian. But what do you like about it? You know, why is it different? I mean, take a few minutes. Actually, the library, who hasn't been to the library? The Law Library of University of Zurich. Hasn't? Yeah, I guess so. It's really great. If you have some friends visiting from outside, show that building. It's for free. You can just enter. So due date, anytime during this course, so I'm not involved in it, you bring it directly to Onur. And later during the course is better, so you can apply some of the principles that you have learned in the course. And the idea is to think out of the box. And before, keep that in mind, you have the slides anyway. And we want to motivate the question a little bit more. So we had this is Bahnhof Stadelhofen. And we have also this. Anybody know where this is? I spent half an hour trying to track down where this is. Because the link is correct. Oh. The link is correct, but the guy didn't really have an idea where he took the picture from. He was too stoned to remember. Anyway, what's the difference between them two? I mean, they are both train stations, right? They are both show rails coming. They both have the same kind of things. But why is, one special and the other one not? What kind of evaluation criteria? I mean, if you're looking at think that you are this city council that is buying a railway station. What are your criteria? What is good? What would you say is important? Yeah?
Swiss railway clock.
Sorry?
The Swiss railway clock.
Swiss-made clock.
The Swiss railway clock.
Okay, Swiss railway clock. Swiss railway clock, why not? What else? I'm just writing it down for myself, you don't have to record. Yes? A roof, so we don't get wet, right? I mean, who wants to wait? Maybe we are in a sunny place like California. Okay, place to stop. But what do you say is better, like, when you want to compare two of them? What kind of things? I can tell you something, I mean, yeah. Cost, yeah, exactly, that's what I wanted to come. You may not want a $4 billion, 4 billion franc tram stop in your city. Okay, so we can take a look at some criteria and you will realize this is actually going to be very difficult. It's a very central part of design and architecture to be able to decide which one of the things is more important for you or how you measure them. It seems very obvious when you look at two and say, I like this more, I like the other one less. Okay, good. But if you want to put a price on it, or if you want to, you have a public approval rating, or if you are building a system and it has a certain cost associated with it, you have to rate and grade your choices. So how to evaluate goodness of design is a critical question. It never has an easy answer, and it will be the same when you're looking at problems related to computer architectures. So how was Calatrava able to design these buildings? What's behind it? Any guesses? Yeah? No. He had a lot of money. Money, which is a very... His father was rich. Okay, what else? Yeah? He was sticking to his principles. That's a textbook answer. Few more? Oh, yeah, sorry. He got inspiration, inspired. You could also say he was lucky to be at the place where he was. somebody needed a commission and his idea struck good, and it could be hard work and other things. But we will be discussing these things a lot. You can list many things, and some of them will be maybe more true in one case or the other, but there are two things. A principled design, a design that was built on some principles, and understanding of and commitment to fundamentals is one of the key things what he was doing. So if you go and look what he is also explaining, how he explains his work, they are looking at, he was inspired from nature. Optimal use of material is the one thing, and the capacity of organisms to shape, grow, and to move. So this is what he said, and his buildings usually have like skeletons of animals or living beings, and they have like this, they are inspired, these are from his drawings for this thing. This is the principle that drives the entire architecture. It's called Zoomorphic Architecture. If you are very interested, you can look it up. I'm just going to skip through. So this is the Oculus in New York City. This is after, the towers fell, they were able to rebuild it, and they said the transit metro station could be rebuilt. So what does it look like? It looks like wings, and it's actually the thing that he was going for. So what he wanted is that a bird is being released from a child's hand, and it spreads its wings and things like that. And people liked it actually, that it was a breathtaking design. It gave new hope. It had some reason and purpose, and people were very happy about it. Remember the constraints that we talked about? So people liked it, but the life of it doesn't go quite like that. If you followed it from the news media, and somebody already said that his designs were very expensive, right? That was one of the things that you noted about Calatrava. It didn't always go the way they wanted. First of all, in the name of security, it had to be changed a little bit. It had to have more ribs. The structures had to be changed a little bit. And now, instead of a tiny and slender bird that is, flapping its wings, people say that it looks more like a stegosaurus, like this thing. Not quite what he had in mind. And then the other thing is that the design was to have like this opening and closing that would allow, some movement into this thing. But then they had to eliminate that thing because of, first of all, budget and cost and space constraints. Still, it cost $3.74 billion without the opening and closing. Okay, so this brings us back to the original thing. There will be, you have some ideas, you have some principles, you have some designs, you want to achieve something in your architecture, but then there are also realities of life, technical limitations, cost limitations, and other things that lets you or forces you to make compromises. And it's also important to understand, to be able to use with these, to be able to live with these limitations and make the compromises when this is necessary. So, Professor Mutlu has been giving this lecture for a few years, and while at CMU, the lecture was slightly different. And you want to see it? Yes, because I have to show it. So, the question was this. Yeah? Yes, he really likes architecture, right? At that time, he was teaching in CMU, which is near Pittsburgh, and this thing is very close. It's in rural Pennsylvania. And when he came here, I was just saying, are you going to show falling water? He says, no, I need some local thing. And I said, Calatrava. And this is why we had Calatrava today. So blame me. But it's the same thing. It's a masterpiece of a famous architect. In this case, it's Falling Water. And it's in all major architecture books, you will see it. And we have the same question here, right? I mean, you look at this, technically it's a house. It's where somebody lives. It has to have a roof, it has to have sanitary functions, very well, you know, water is flowing underneath it, and maybe some amenities. But if you just look at the function of it, it's the same as any old wooden house that's in the woods. But that's not it, right? It's just a house. There were some principles behind it, and this is now the important thing, maybe to latch on to. The architecture was based upon the principle. He had some principles going and making this design. And it was not based upon precedent. It wasn't like, oh, people build houses like this all the time, so let me just go and build another one of those houses. That wasn't his idea. He said, I have a principle, I think the architecture of this thing should be based on it, and I want to make sure that this is this way, and not copy the same idea. I'm going to build something what I have. And his principle in this case is what you call organic architecture, which promotes a harmony between the human habitation and its surrounding, and you try to blend in your world into the nature as much as possible. So there are also other things, other famous buildings that are made this way, and we come back again to the same principles. How was he able to design his masterpiece? You can again have the same discussions, but principled design and understanding of the commitment to fundamentals is again the most important takeaway here. So it's what you should take. I mean, why did we do this excursion to the architecture? It's an example, okay? It all starts from your basic building blocks and your design principles. You have something in your mind. If you're an architect, you have the basics of statics, basics of the requirements of human habitation and things like that. And then you have your design principles that will allow you to guide to a finished product. And not only that, it's not enough that you have that. You need to understand and know how to use and apply them. And this is now the interesting thing. The underlying technology that we have for making these things could change over time. So, you know, you could be building first with steel, next time with concrete or with wood. That's not the thing, but the method, the way you approach the problem, the way you try to solve the problem, that one stays the same. And this is the thing that we should be understanding. This is also one of the reasons why we can give an example from a completely different field and still be talking about or making some conclusions about our own field. So the same actually applies to processor, to computer chips, to what's inside the computer. There are basic building blocks, and there are some design principles in these things. So these are the building blocks inside your computer, but it's not only inside the computer. So they then end up making your computing systems, be it something handheld. You know why I hate Moore? Mr. Gordon Moore? Any ideas? You know how annoying it is every year to have to change this picture because it looks outdated? I mean, if I was teaching an architecture class and giving examples from chips in this thing, I wouldn't have to change the bridges in the background. I could always show the Golden Gate. But, yeah, okay. The same applies also, you know, you start from small computers, but it doesn't matter if you're looking at a handheld device or a, you know, personal computer or a large data center which has thousands of computers inside, and those computers have tons of different things. It might be different platforms. So this is a mobile thing that flies around and maybe does something useful. The platform may be different, but the principle, so to say, is more or less the same. So this is, in case you don't know, this is one of the first Google Street View cars that they had. So we will come and we will talk about in this lecture from our basic building blocks. So we have electrons, transistors, logic gates. We will continue, the electrons and transistors we will not touch so much, but combination logic circuits, sequential logic circuits, they all sound Greek at the moment. And then we will end up with the fun part, cores, caches, interconnect, memories, the things that make computers. So the parts that you should be looking, the textbooks and other details are on the web page. I will talk about that in the second hour. The reading assignments are from the Digital Design Computer Architecture, the Chapter 1. And if you have access to Introduction to Computing Systems, the first 2 chapters, to give you some information and some insight into the computer architectures in general. So the high-level goals, what we want to achieve, what our goal is for specifically for digital circuits and computer architecture, you should understand the basics. It's not like people will need you to design computer chips or design electrical engineering specialty things. But it's good if you know what they are doing, and it's good if you can just go and say, it's not a big deal, I know how to do it. I'm just smarter, I'm not doing it. I choose not to do it, okay? Understand the principles of design, because those principles actually are more than, or tell you more than, what the current specifications are. It's not that it's 3 gigahertz, 2 gigahertz, 500 megabytes, gigabyte RAM, hard disk, SD RAM. It's important to understand what's behind them, what prompted that we have, 3 levels of caches, what prompted to have multiple cores, and understand how the thing evolved, what kind of problems forced us to make these compromises, these decisions. And we will, based on this understanding, you will be able to grasp how a computer works internally, how these things are done, and you will be able to evaluate trade-offs of different designs and ideas. We will talk about it more next week also. The goal at the end of the lecture, as part of the exercises, is also to reach for us to a level that every one of you can build a small, simple microprocessor, and not a very simple one, a simplish microprocessor that works. Sounds great, right? Hey, your own microprocessor. I lost you at the architecture, right? People are still planning their trip, okay. One of the problems of trying to design something complex is, and don't lose hope when you're doing this in the exercises and other places, you try to design something complex, you push the button, and it doesn't work immediately. That's not something that should set a panic in you. That happens. The important thing is that you should know how to deal with these complexity, and this understanding should also enable you to develop novel, out-of-the-box designs. So the focus, we will talk about a lot of things during these classes. We will show you a lot, but the takeaway are maybe not the details. What you should be focusing are the basics, principles, precedents, how did it come to be, and which one of these things resulted in good designs. Notice that the good design is still debatable, because we have to still come up with definitions of what is good, or what exactly do we define as good. So why these goals? Why are we having these lectures? Because here you are for a computer science degree, and regardless of your future direction, you could be concentrating on databases, you could be concentrating on more theoretical aspects, you would want to do IoT systems, security, whatever. The principles of digital design and computer architecture will be useful. You'll be able to design better hardware, or be able to talk better with people who are designing the hardware. If you understand the hardware and the limitations, you'll be better in a position to take advantage of it than people who don't know it. You can make better trade-offs in design, and once you see strange behavior or things you cannot understand, it's not like the computer doesn't like me. It will be, you know, why we are doing. Okay, after the break, we are going to talk a little bit more about these goals, and then also give you some administrative information about what we are going to do, what's the exam, what will be asked in the exam, and things like that. So see you in 15 minutes. Okay. Is this on? Yes, we can hear each other. Perfect. Perfect. Okay, so we were talking about the goals of the lecture. I can tell you that in your lectures at ETH, you will see professors especially trying to emphasize these things. What are the learning goals of this lecture? Do you realize that in classes that people put some slides like that? No? You know why? Nobody? Okay, at the end of most semesters, they ask you to make a class evaluation. And part of the class evaluation is, you know, was the person able to speak coherently? Was the class nice? Did you spend time on it? And things like that. And one of them is, did the lecturer make it clear, the design goals, the Lernziele, did he make them clear in every lecture? And if you are at ETH and you are teaching, this is like one of the things that everybody gets a lower grade than everything else. Because students are saying, whatever, he said something, you know. So this is why we are trying to make sure that these are here, because we are also working for grades. And just to tell you something, it's important. I've had a lot of discussions with students at ETH who think that these things do not matter. They do matter. The feedback that you give after lectures is very important, because when you are in teaching, you are sometimes lost. You realize that you're not coming across. You realize that maybe the performance is not good enough, or something, and you're actually looking forward to it. And you don't want to always say, the lecture was great, you're so nice, and things. It's nice, it's flattering. I mean, we like it. There's no lying about it. But it's the honest responses that help us make the lecture. And usually the turnout is not so good, so about half the people, or 1/3 to half, answer it. And usually the people who hate it absolutely, and the people who are in love with it for some reason or the other, respond. But the majority doesn't say much, and sometimes decisions are made by the responses you get from that. So it's important, try to be active, and contribute to these things in all your lectures. It might be that you have the feeling that some of your lecturers do not take that seriously. Most do. We talk among each other. We sometimes say, hey, we didn't get any feedback. What do we do for? We are also clueless in some cases, okay? So also try to do your part. Okay, so back to the class. One of those questions that we should be asking is, why do we have computers? Wasn't life better without them? Philosophical question. Any answer? Yeah?
They compute things.
Right. They compute things. It's yeah. They make our lives easier. They compute on their own, right? Or why do we do computing? That's the other thing. They make our lives easier. Or one answer could also be, we use them to solve problems. There are problems that we can only solve. One of the better ways we are solving is by using computers. And actually, if you look more into philosophical parts of it, you want to gain some insight. You want to gain insight about the whys. Why is this happening? Why are we doing these things? What can I learn more from it? So to have this insight, to solve problems that affect humanity, that affect us, the society, or our financial dreams, whatever, we want to do this. And ultimately, if you have high ideas, high morals, you may want to make the idea to enable a better life and future. Is it? No? It's looking at me saying no. Not at all. I don't care about life and future. God damn it. I cannot repeat that. It's a recording. But, no, sorry. So, how does a computer solve problems? Well, the short answer to it is, these days, orchestrating electrons. There are these nice electrons inside your computer, in the chips, and we are telling where they should go, what they should do, and what kind of, those interactions, ultimately, I mean, looks like a joke, but it is true. It's actually, you have 10 billion transistors. Each transistor opens and closes, and let's say, flow of electrons go through them, and by orchestrating their movements in this entire mini universe, a modern computer chip that you have in your laptops, in your data centers, is about 2 to 3 centimeters on a side. So the largest chips that you will see are about this big. There are 10 billion small parts in it, and each one of them controls the flow of electrons. And there is when you talk about a computer, you talk about speeds. Anybody know how we express the speed of a processor? Some hertz? Who said yes? Flops, floating operations per second, yes, but there's another number when you go to MediaMarkt and you want to buy, they are saying hertz. And not 1 hertz or 2 hertz, but giga. So giga is 10 to the 9, it's a billion, right? It's 1,000 million. And when you say, for example, something like 2 gigahertz, what does it mean? It says it does operations 2 billion times a second. Within 1 second, you are doing 2 billion operations on 10 billion transistors. It's a crazy number. It's completely out of this world. And you know what? Now I'm putting my EE hat, just to give you some perspective. What's the fastest speed you know of? Somebody said something. Light, speed of light. Who agrees that speed of light is fast? You will be wrong. One of our main problems, this is the electrical engineering, Frank speaking, is the speed of light is extremely slow. It is very slow. I can give you an example. Your processor works at 2 gigahertz, right? Who has a computer that works faster than 2 gigahertz? You don't know, I don't care what's the answer. Okay. A lot of you do. 1 gigahertz means that you're doing, let's stay at 1. 1 gigahertz means that you're doing things 1 billion times a second. If you look at the time that your processor does 1 unit of operation, that is 1 nanosecond, 1 billionth of a second. It's like a number that you hear a lot, 1 nanosecond, 2 nanoseconds. It's, slightly smaller than the microsecond, slightly more than the picosecond. In 1 nanosecond, do you know how much light travels? Quick, Google, up, no? Any guesses? Okay, here it is, 30 centimeters. This laptop, 30 centimeters on the side. That's the speed of light. Within 1 gigahertz, within the time a 1 gigahertz processor works, light in vacuum travels only 30 centimeters. It's not able to come from this corner of the screen to the top of the screen. If you are working at 4 gigahertz in vacuum, you will only manage to go 7.5 centimeters. Not an impressive speed. And this is in vacuum. If you are there's nothing interacting with it and light is traveling. Electrons traveling on a wire, which is, disseminating energy around it, travel roughly at 6/10 of the light speed. So you're even looking at something like 4 centimeters. So if you want to talk about relativity, me standing a meter away from a 1 gigahertz processor, the moment I see it, actually, it's already 3 clock cycles ahead. He has already done 3 operations the moment I saw it. Maybe I saw it, the computer exploded. So light speed, well, it is very human. I mean, it's a very annoyingly slow speed, especially after Moore and the others pushed these laws on us, and we, improved things further and further. Transistors went faster, transistors went smaller, we could do more, and now we are reaching physical limits, and unless there are some changes, we are stuck with those limits. This is also why Onur put here at the very bottom saying, in today's dominant technologies, it's orchestrating electrons. Moore's law is an exponential law, and if you understand about, infinite series and, limits and things like that, it's pretty obvious that it cannot go on for, let's say, 1,000 years. The people who were saying Moore's law realized that, okay, within our lifetime, it will hold, and I don't care what the students do afterwards. And so maybe in the time when you are my age and teaching these classes, it will no longer be electrons, but some other things. So, but now let's stay with the electrons and how the problems get solved by electrons. So we are coming back, actually, to our transformations. And the inside code actually comes from Richard Hamming. Anybody heard of Hamming distance? Oh. Why? Okay, this is Mr. Hamming and his cat. Not to be confused with Schrödinger's cat, which is different. And it's his thing is we gain and generate insight by solving problems. I mean, this is his, what he was preaching. There's actually a lecture, we'll come to it in a few seconds. And here's the question, how do we ensure that our problems that we are facing are solved by electrons? So this is what we are looking at. So at the very, very top, this is the same abstraction levels we were looking at. We have the problem. And at the very bottom, we have the electrons. So somehow, these two will have to connect. Okay, sorry, I thought it was a question. Some people are enjoying this class way more than they should. It's good, I feel good about it. Okay. Is there still people in the other class? I have no idea. They probably said. They are? Do you talk to anyone? No. Is that segregation made? We are the other side. Okay, so the first thing is, to solve the problem, we resort to algorithms, and we have a step-by-step procedure that tells us how we can come to a solution of this problem. So this is a precisely formulated step-by-step solution to the problem. We worked this out. We said, if you follow these steps, in the end, you will have a solution to your problem. The good news is, if we can have this nice description, not a vague, you go out and count all the people in the classroom. No, if you have a precise way that tells you step by step how to do things, you can actually carry this out by a computer. So there is, it's finite, it's definitive, and it can be computed. The good news is also, there's not one algorithm to solve most of the problems you face. There are some which have just one obvious solution, but there are many different algorithms that can be used for the same problem. Maybe they have different trade-offs between them, but this is a step in between that you are interested in. Now, once you have the algorithm and you know what to do, you have basically the complexity of the problem, you know the steps that you have to do, you need some means of doing that. So the programming language, or the program and the language it's programmed in, is a means of achieving that. The next level is that what you have is then running on a operating system that allows you to have access to the resources of the computer, the network, the memories, lets you run different programs at the same time, gets user input, communicates, and provides you the capabilities, the ins and outs of the computer. And then the next level is what we call the instruction set architecture. The instruction set architecture, which is going to be one of the major parts of this course, is a contract between the hardware and the software. You agree what the capabilities of the hardware are, what's the alphabet, what's the language that it speaks. If you have an agreement on it, the hardware people can implement a processor, a system that has a physical implementation of it. And on the higher levels, you can develop your programs, your algorithms, write the programs, and map them to the same alphabet that the hardware is able to understand. So this is a contract between the two. And this is also going to be the one part, or one of the lectures where you learn more about what this interface is and what lies underneath. Now, once you have defined it, once you have defined the ISA, the one that I was talking about, RISC-V, for example, is such an instruction set architecture. It's more or less a description of rules. It says, this processor understands 50 commands. The first command is called add. It takes 2 numbers, and it adds these 2 numbers and writes it down to a third one. Or this one is called jump, and you give it an address, and it's whatever jump is, does that thing. The microarchitecture on the other side is a real implementation of it. It's the first one was a contract, the other one was a drawing, was a sketch, the other one is actual building of it. And once you start building it, you'll have to make some decisions. It will take physical form. Some of those instructions, as we said, will take more time than the others. Some of them will be easier to do than the others. Some of them will introduce problems. And if you go one level below, this microarchitecture will be built using elementary building blocks, digital logic cells. They are really not so spectacular. ANDs, ORs, full adder, XOR. Who likes these things? There are still classes available in electrical engineering. You're welcome. We can talk more about the details of ANDs and ORs in there. But okay, technically, these are the basic building blocks. And underneath that, we have devices. So it's not only, we will be mostly talking or always insinuating that we use transistors. You will hear that they are CMOS, complementary metal oxide semiconductor devices, has a long name. There could be other implementations of it. It just happens to be that in the last few decades, this is the most efficient way of doing it. And those devices at the moment control electrons. And so this is how we close the gap. So if we, again, look at the problem and the electrons and your entire hierarchy, if you strictly look at computer architecture as a narrow view, this is what you'll be dealing with. And most of the books that you can buy, or most of the courses that you visit on computer architecture, will want to concentrate on this thing. What's the instruction set architecture? How is it defined? And how is it then implemented in logic gates, adders, memories, and basic building blocks? How do they come together? What are these things? What we want to do in this lecture is not to stay here, because we were talking about it, that we need to take an expanded view of these abstraction levels, not only limit ourselves to what is happening here, we need to take a broader view. So this is the main goal or main challenge that Professor Mutlu wanted to address as part of this class. So we could have limited ourselves only to this, but his point, and also I agree with that, is that to be able to become better scientists, better engineers in the computer science field, you have to know more and expand your horizons from strictly this part and be able to look at the architecture in a slightly larger way. So just to give you also a few insights about the man that shaped our fields. So Hamming is famous for his work in the 50s, the error detecting and error correcting codes. It's a brilliant field, actually. You realize that ideally, this is also the problem, right? You say, I don't want to make any mistakes. I don't want to lose any information. I want to store everything. I want that all students like me, things like that. And so soon you realize and hit the reality, and then you realize it's not going to happen. Transmissions are not going to be very efficient if you can never tolerate a mistake. And then you say, we can be clever about it. We can build in codes that detect that there are some errors and even are able to correct it. And a lot of the work here, Hamming is one of the pioneers. You might also know him from Hamming distance. Hamming distance? Yeah. Why is Hamming distance so well known? I mean, yeah? Aha, you had it in discrete math. Okay. I should have studied the other lectures. I was trying to give you some more insight. So it's the number of locations in which in a equal length strings are different. So if you're looking at binary sequences, number bits that are different. And he developed a theory of codes and used it for error detection and correction. So if you're really interested, there are some nice talks. Not all the people that have contributed well to the scientific community give good talks. It's true, you know, some people are very famous, they did a lot of works, but you watch them, or you go to a TED talk or whatever, or you don't find them there. But some of them actually have very good insights, and it's interesting, you think that the more you're in the field, the more complex formulas and the more complex explanations will come. It's actually just the opposite. You reach clarity and you're able to explain the problems and the solutions to it more simply. So you realize that the person has reached some maturity in which he tells it. So, okay. This is about Hamming, but I know that you are more concerned about the course. So let's give you also some practical information in the last 20 minutes. The course is a website. Everybody visited the website so far? Excellent. So there will be lecture slides and videos. You're recording this? Okay. I'll forget this part. Okay. Okay. Readings, lab information, course schedule, information, and this is actually your single point of access. All things, all resources about this lecture should go over this website. This is important. You'll be able to reach the lecturers, teaching assistants, everyone equally when you use the Moodles and the mailing list. So we have lectures and lab sessions. Lectures are Thursdays and Fridays in this room. Seems to have worked. F5. I really feel bad about the people, but I'm sure they're having a great time over there. I think the underneath screen shows F5, right? No. It's okay? No. Well, sorry. There's still the splash zone is empty. Yeah. Well, somebody already asked me, is the video going to be online? Do I have to really come? The answer is yes, the videos are going to be online, and no, you don't have to come. I mean, I think it's for your benefit, and I think we try to make a more interactive lecture and try to highlight things just than having boring. If there was nobody in here, I don't think we could emphasize the same things. You get some feedback from it. I don't know. Come, please. Sometimes, some days, like today, we will have guest lecturers and even exercise sessions. And for lab sessions, I'm going to have you have some more information. Actually, next week, we are going to have an hour where we only talk about what we do in the lab. But you should definitely visit the lab sessions. Lab sessions are cool. We are putting a lot of effort into the lab sessions. They will start on March 5th because we still have to organize the access to it. And once again, from the website, you'll be able to go and find information about the labs. Now, the course information, we already talked about Professor Mutlu. He's one of the most published authors in computer architecture in the past few years. He works at most major companies, and if he hasn't worked at one, he certainly had collaborations with the rest of them. So he worked at Google, VMware, Microsoft Research, Intel, and AMD. And he's very accessible through email, so the best way to reach him is to use his Gmail account, and if you want to arrange an appointment, again, use the email to access him. He has a broad spectrum of research that he's interested in and is very active. I will be talking about 4 topics that are related to what we do tomorrow. So tomorrow's lecture will be about things that intersect what we want to do, explains why we need to look further than the abstractions levels we have. And there's a large group of, a small army of assistants that will help you with. That assistant is one. He's the boss. And he's such an important boss that he also has a vice head assistant. And many more. And we also, for the exercises, the last time I checked, there were 450 students registered to the course, which is great, but it puts a lot of effort for supervising the exercises. So also do not forget, in the coming years, if you like the lecture, if you enjoy the laboratories, we will also need your support to be able to do the exercise in the upcoming years. We have some great lab sessions. They are excellent. We will be using an FPGA board, field programmable gate array. You'll learn all about it. But technically, in the middle of it, this person is a programmable device that lets you implement any circuit that you can dream of. And in the end of the lecture, in the labs, you'll be able to run your own microprocessor running on this thing. And this is like that sort of brilliant thing that lets you do a lot of cool things. There are push buttons, there are buttons, and then there is this counter. You see this? 7-segment display. Have you ever seen a Hollywood movie where a bomb doesn't have that? No. And in all Hollywood movies, they are always accurate. There's no bugs, there's no, I'll explode at 2 minutes, 14 seconds. No, they all count down perfectly. And I'm not suggesting you build bombs, but this allows you to make nice and small things. We have many students. As I said, 400 students. It's not possible to have you all in one room. This is why we have several sessions. And over the years, people have their own preferences. Everybody is already looking around. No, I don't like that. I don't like that. So Tuesday, 3 to 5, Wednesday, 3 to 5, Friday, 8 till 12. We'll have 4 different sessions. And as I said, at the end of the exercises, we will have built a 32-bit microprocessor that is running on this FPGA board. It will be a small processor, granted. It's not like a Pentium, or you can, boot Linux on it or something like that. But it is much better than anything that went to Moon. Okay? So we were able to people were able to walk on the Moon with processors that are not as good as the one that you'll be able to build. Yay? No. It's good that I only have 15 minutes left because, I'm losing the class. So each week there will be a new exercise. We try to keep the exercises short and concise so that you see an aspect of it. Not every week will we be able to use the FPGA boards. We try to make the exercises so that you get more access to it, but it's not always possible. Just also devise an exercise about it that you use the FPGA boards as well. But you will get your FPGA board. I mean, you will be working in groups of 2, right? And you will have your FPGA board. You can take it home. And if you are interested, we may even have some extra that you can work with. And you know, this is great. You can play with them. And I can guarantee you, now take it as a challenge, it is not possible to destroy the board by programming. We'll see about that. No, I mean, I'll go back. This is a company, Digilant. We use their boards for many years in education. They are a Taiwan-based company, Taiwan, Romania, US-based company. And they started it for their own lectures. And the boards are really robust. It's not very easy to destroy them by programming. And before you try, jumping up and down on it is not programming, okay? If you attach a programming cable, type in something, it's not going to burn. Challenge accepted. So, as I said, next week we will have a lecture where we talk about the exercises more in detail. Important thing, most of you have received some emails through the Moodle system. I already heard that some people complained they haven't. If this is the case, you can use the links on the course website to contact the assistants and say, hey, there is this Moodle thing, I haven't received it, what gives? And you will get it. The first thing that you have to do, and it's important, is to choose your preferred group. What time do you want to do it? The second thing is, you don't do them alone, you'll do it in groups of 2. And no, if you have your bestest 2 friends, you cannot do in groups of 3, you do it in groups of 2. Grow up. And you have to choose your partner. And there are deadlines for establishing the groups. I think there is a very sophisticated algorithm that pairs off the people who don't have a group partner. Very sophisticated methodology. There might be some people who are repeating the class, and they have already visited the labs, and you can decide on what you want to do. There are 3 options. So you can say, I will use my lab grades from previous years, and I want to do the labs this year. So this means that I already did the labs, they were great, I loved them, and I got a decent grade, and I want to keep my grades towards my final grade this year. I won't spoil anything. And there is a version that says, I will use my lab grades, but I like it there, it's nice, and I want to do them again. And the third option is, you know what, last year didn't exist, it was a blip. I will redo everything, I want a redo, I will do much better this year. If you use 1 or 2, there is a difference in the way they were graded, I believe, so it will be scaled. And if you do 3 anyway, you are going to get a new grade and you say bye-bye to your old grade. Sounds fair? Turn serious. Now, the final exam. Something that nobody is interested about. At the end of the semester, in the regular examination session, there will be a 3-hour exam as part of the session. So if you look at the rules from the course catalog, 70% of your grade will come from this exam. And then 30% of the grade will come from the exercises. So during each exercise, there are 10 of them. Each of them more or less gives you 3 points. Or you can think that it gives you 3 points. They will be accumulated and added to your exam grade. Part of this is to make sure that you attend the exam sessions, because we think that, or we believe, that you learn a lot in the exercises. This is also why we are willing to invest more time in making the exercises interesting. And there is no live video stream of the exercises. Come, touch the board, be in the lab, do the things. For the exam, there are no books, computers, mobile phones, calculators, any form of electronic help allowed. So some people get stressed, therefore we allow them to have 6 A4 pages with handwritten notes are allowed. The exam will be available in German. I mean, it's in the course catalog, so it is available in German. There's no 2 ways about it. But it will also be available in English for those people who prefer it. Before the exam, we will make a survey to ask you to choose one. and we will print the exams accordingly with your name on it. So once you make the decision, you say, I want the exam in German, then the exam will be given to you in German. If you say, I want it in English, it will be given in English. This is to make, 450 exams. We are not printing double of them and distributing them there. As most of the class and the slides and the exercises will be in English, there is a benefit maybe, or you'll be more familiar with the English version of the exam, but still there is absolutely no problem in having the exam in German, and I believe it's also not a problem if you have the English exam and still answer a few questions in German. Is that correct? Or Turkish? No. So the previous exams are available online, important thing. And another thing, we will have some optional homeworks during the lectures. And people say, yeah, optional things are optional, I don't care. The important thing about optional homeworks is they are very similar to the questions that you will see in the exam. So if you are doing well on the optional questions, there is also a good chance that you will do well in the exams. It will help you to prepare for the exam a bit better, so you know what to expect, what kind of questions are being asked. You can see that. So the optional homeworks are highly recommended, and if you are having problems with it, use the Moodle. Also help discuss among each other. That's the idea about the Moodle, that we have a community to discuss things. If you need any help, the questions on the Moodle Q&A is the preferred way for the technical questions. You can also write an email to digitaltechnik listinf.eth.ch. Everybody who is in the teaching, who is in teaching duties will receive this email, and it's better than writing to people individually, because if multiple people receive it, the chances of somebody answering to you fast is much higher than elsewhere. Okay, so this is actually the part that I want to talk about today. Are there any questions about the exam or the lecture in general? Everybody's looking at it, say yes, we have to stay longer. So tomorrow we are going to take a deeper look at 4 different mysteries of computer science. Give me a second. And we want to see how problems get solved by electrons, and I'm just going to skip ahead some slides. Yes, okay. We will talk about these 4 specific cases. The first one is a bit of information about meltdown and spectra, what lies behind it, what is causing this, and how it can be solved. And we are going to talk about Rowhammer, memory performance attacks, and the issues about refresh in memories, and what can be done about it. So tomorrow we are going to go over these problems, each roughly half the lecture, to see what can be done. I thank you very much for being with us here, and tomorrow, see you again.